Sorry about that. So resuming our discussion, does water have polar bonds? Yes, definitely. The oxygen-hydrogen bond is quite polar. Okay. Does oxygen have a lone pair? So one, we have polar bonds. And two, oxygen has a lone pair. As a result, this molecule is polar. We can clearly see that if we add our dipoles together, we have a net dipole. So water is polar. So let's do a few examples before we close out. So let's draw the Lewis structure and overall molecular dipole for the following molecules. So I'll do these first two and you'll do the next two. So for hydrofluoric acid, the hydrogen-fluorine bond is polarized towards fluorine. So this molecule clearly is polar. For CHCl3 or chloroform, we have carbon in our center surrounded by hydrogen and 3 chlorines. Okay, we fill out all of our lone pair electrons. And now I need you to think really carefully now. When we think about polarity, in order to draw our bond dipoles, we need to know what our molecular geometry is. So what is the molecular geometry for the following molecule? What is the molecular geometry centered around carbon? Would someone like to share that in the chat? What is the molecular geometry centered around carbon? And I've already drawn this molecule in a very suggestive way to help you elucidate that. We always need to think about our molecular geometry and how it relates to polarity. If we have a steric, what is our steric number in this case? Steric number is 4, so this is tetrahedral. So then to draw this a little more suggestively, this molecule looks something like this. Now, when we think about our polar bonds, our carbon-chlorine bonds are polarized towards chlorine. Let me angle this a little bit differently to make it very easy to see what's going on. So, looking at this molecule, where are all of our dipole arrows pointing? Are they pointing up or down? Just qualitatively here, where are all of our dipole arrows pointing? Are they pointing up or down? Are our dipole arrows pointing up or down? Just looking at all of our bond dipoles. What does it look like? So looking at all of our bond dipoles, what do we see in the chat? Are these bond dipoles all pointing up or down? Are they pointing in one direction? Are they pointing in opposite directions? What do we think? They're all pointing down, exactly. So our net dipole is likely pointing down towards our region of our molecule with all of our chlorines, the region of our molecule with all of our electronegative atoms. So this molecule is clearly polar. Does this example make sense to everyone? Yes. So if we think about the tetrahedral geometry, I'm going to turn on the webcam to help you see this, so that way it's a little more clear. Okay. So if we look at the tetrahedral geometry, do you notice how all of our chlorines are on the bottom side of our molecule? Like all of these white spheres that we'll use for chlorine? Yeah. So all of our bond dipoles are pointing towards chlorine. So are they pointing up or down? Down. Exactly right. Does that make sense? I find it's always easier when you think about these molecules in terms of their 3D shape. And that's why we talked about geometry before we talked about polarity. Perfect. So let's do one last example to wrap up this lecture module. So I'd like you to draw the Lewis structure for the following molecules, and I'd like you to draw the overall molecular dipole for the following molecules. And we'll discuss this example in about 3 to 4 minutes. Thank you for sticking through this supplemental lecture and problem solving period. And this will be the last example set that we'll be doing today. And we'll discuss this example in about 3 minutes. Okay, so let's discuss this example. So this common molecule that's often looks like almost also a principal component of refrigerating agents, almost looks like a refrigerating subcomponent, or, oh, never mind, not a refrigerating component. This compound is actually quite interesting as it's a very reactive oxidizing agent. There have been a lot of blog posts and chemistry blogs about this specific compound. But what's important is that we start to look at how different polar bonds can interact and influence our net molecular polarity. So then, quickly drawing the Lewis structure for this molecule, I'd like you to tell me, what is our molecular geometry? What is our molecular geometry looking specifically at carbon? What is our molecular geometry? If we have 4 bonded atoms, what is our molecular geometry? And don't be shy to consult the table. Tetrahedral. Okay, perfect. Now we draw all of our bond dipoles. So we have 3 chlorines pointing down, 1 fluorine pointing up. Okay, so thinking about our push-pull dynamic, if all of our chlorines are on the bottom and our fluorine is on top, my question to all of you is, and this is really important now, oops. So if all of our chlorines are on top, if all of our chlorines are on the bottom and our fluorine is on top, if we have multiple polar bonds on the bottom, what's going to win out? The 1 polar bond on top or the 3 polar bonds on the bottom? What's going to win out? The 3 polar bonds on the bottom. So our net dipole is going to be pointing down towards our chlorines. And this clearly is a polar molecule. Finally, looking at ammonia. So for ammonia, ammonia's Lewis structure looks something like this. Yes, the carbon-chlorine bond is polar. There's a difference in electronegativity. Looking at the nitrogen-hydrogen bond, we have multiple polar bonds polarized towards nitrogen. So where is our net dipole going to point? Towards nitrogen or hydrogen? Where is our net dipole going to point? Where is our net dipole going to point? It's going to point up towards nitrogen. Exactly right. And just as a side note, this molecular geometry for ammonia, what would the molecular geometry be for ammonia if we have 3 bonds plus 1 lone pair? What do we call that molecular geometry? What do we call that molecular geometry? 3 bonds, 1 lone pair. Trigonal pyramidal, exactly right. Perfect, perfect. No. It's polar regardless. As long as there is a net dipole, it will be polar. If there's no net dipole and your dipoles cancel, then it's nonpolar. Does that make sense? So the direction doesn't matter, just the fact the dipole exists. So if we compare carbon and chlorine, so the carbon-chlorine bond is polar because there is a substantial difference, there is a non-zero difference in electronegativity. The only case where you have a non-polar bond with a difference in electronegativity would be a carbon-hydrogen bond. And that's because depending on the exact electronegativity table that you look at, your electronegativity values will be a little bit different. The only non-polar bond that has atoms of different elements that you'll see a lot is the carbon-hydrogen bond. Every other bond, especially a carbon-halogen bond, that bond is polarized. That bond is definitely polar. Even though the electronegativity value, if you calculate it from the table provided, doesn't quite seem large. So yes, carbon-iodine bonds are also polar. Yep. Perfect. Okay. So I'll post these recordings to Canvas.